Welcome back, Physics 30. So we had the introduction to the special theory of relativity. So now we'll look at 26-1, Galilean Newtonian relativity. So we're going to look at this first section here. It'll likely take a few videos, and then we'll go from there. Alright, so Einstein's special theory of relativity deals with how we observe events, particularly how objects and events are observed from different frames of reference. So, of course, we looked at frames of reference. Frame of reference is a set of coordinates fixed to some object such as the Earth, a train, or the Moon. So whether we're talking about the Earth, a frame at rest, or a frame moving with constant velocity, that kind of leads into the idea of inertial reference frames. That's what we're talking about here. The special theory of relativity deals with events that are observed and measured from the so-called inertial reference frames. And we talked about that in the earlier section 4.2. So frames that are at rest, or frames that are moving at constant velocity. But your reference frames in Newton's first and also Newton's first law is valid. An object at rest will stay at rest in these frames, or an object in motion moving with a constant velocity will maintain that motion. If, of course, the object experiences no net force, no unbalanced force, which happens when bodies start accelerating. The object either remains at rest or continues in motion with constant speed in a straight line, which is velocity. It is usually easiest to analyze events when they are observed and measured by observers at rest in an inertial frame. The Earth, though not quite an inertial frame, because the Earth rotates, we're rotating, so technically our velocity is changing because our direction is constantly changing, but it's close enough that for most purposes we can approximate it to be an inertial frame. Rotating or otherwise accelerating frames of reference are non-inertial frames. Just be wary of that. And won't concern us in this chapter, but we will look at that. We will look at frames that are accelerating when we talk about the general theory of relativity, because that comes into play there. A reference frame that moves with constant velocity with respect to an inertial frame is also an inertial frame, since Newton's laws hold there as well. So an object at rest will stay at rest, an object in motion will stay in motion with constant velocity. Okay. The next page here. Both Galilean and Newton were aware of what we now call the relativity principle applied to math, which means the basic laws of physics are the same in all inertial reference frames. So what happens in one frame, those same laws apply to the second frame as well. You may have recognized its validity in everyday life. For example, objects move in the same way in a smoothly moving constant velocity train or airplane as they do on Earth. So the video that we saw previously, or maybe it's in the next one, if you drop a ball, if you're standing still and drop a ball, it falls straight down. If you're moving in a car that's moving at constant velocity, i.e. same speed and in a straight line, that ball just falls to the ground by you witnessing that event. So when we talk about that example, now suppose you're in a car traveling at a constant velocity, so maybe going 100 kilometers per hour straight. You drop a coin from above your head inside the car. How does it fall? So of course it just simply falls straight down with respect to the car and hits the floor directly below the point of release. So you dropping the coin, you would see it just simply fall straight down, and that's from your frame of reference, the reference frame of the moving car, which of course is an inertial reference frame because you're moving at constant velocity. Okay, and that's how objects would fall from someone just doing the experiment on a place of rest. Note in this example, however, that an observer on Earth, the coin does not follow that. In that earlier 1960s video we saw, they demonstrate that well with the cart and the ball bearing being dropped. So when the camera is attached to the moving car or that cart, we see the ball falling straight down. And furthermore, we have no way of, unless we see the background, if it was just a white background, we would not be able to determine whether that cart or car is moving or not. It's just that when we see the background moving, we can determine whether it's moving. So anyway, and then when the camera is fixed to the Earth, we see the car go by, it's actually following a curved path like that, not simply falling straight down relative to someone on the fixed Earth. So it's a curved path. The actual path followed by the coin is different as viewed from different frames of reference. This does not violate the relativity principle because this principle states that the laws of physics are the same in all inertial frames. i.e. the same law of gravity and the same law of motion apply to both reference frames. The acceleration of the coin is the same in both reference frames. The difference is that in A and B, the Earth's reference frame has the coin going at an initial horizontal velocity equal to that of the car. So that's what I added up here. So according to the person inside the car, there is no horizontal motion of the coin relative to the man. It's just simply the laws of physics, and what we'll see in projectile motion when we study that in Physics 30 is that its initial velocity is 0, falls straight down. But to someone on the street would see, oh no, that car is actually going with an initial horizontal velocity equal to that of the car. So if you're just to keep an eye on the coin as it's falling straight down, it would actually follow a curved path like this to someone observing it from the fixed ground. So the laws of physics therefore predict it will follow a parabolic path like any other projectile, as we'll see, and that's in fact what happens in this scenario right there. So the laws of physics apply equally in both of those inertial reference frames. In the car's reference frame, there is no initial velocity, and the laws of physics predict that the coin will fall straight down, because that's what happens when we have no initial velocity. But of course, if we have an initial horizontal velocity, the laws of physics apply in that there'll be a curved, a parabolic shape. And we'll look at that when we go back and study that in Physics 30. So the laws are the same in both reference frames, although the specific paths are different. Okay, so just like over here, the laws are the same, but the paths may be different in different reference frames. Okay, Galilean Newtonian relativity involves certain unprovable assumptions that make sense from everyday experience. It is assumed that the lengths of objects are the same in one reference frame as another, and that time passes at the same rate in different reference frames. And for the most part, when we go back and study some of the other material here in Physics 30, we will see that time is constant, and the lengths of objects stay the same. So there we're implying that, hey, maybe with special relativity those things change. Time isn't as absolute as we think it is, and lengths of objects can change, which is extremely weird. So length and time intervals are absolute, so that's pre-relativity, and in most of our situations, traveling at far less than the speed of light, that is true. So in classical mechanics, then space and time intervals are considered to be absolute. Their measurement does not change from one reference frame to another. The mass of an object, as well as all forces, are assumed to be unchanged by a change in inertial reference frames. The position of an object, however, is different when specified in different reference frames. As we saw up here, the position of the coin falling straight down here. Here it's a curved path, so that is different in different reference frames. For example, a person walking inside of a bus towards the front at a speed of 2 meters per second. But if the bus is moving 10 meters per second with respect to the Earth, the person is then moving 12 with respect to the Earth. And of course, that was one of the first things that we saw here way back here with the train example. So different reference frames would be described slightly differently. And of course, Newton's laws hold true in both of those frames, no matter what they are. Okay, and back to here. So that describes that. Accelerations of an object, however, is the same in any inertial reference frame according to classical mechanics. This is because the change in velocity and the time interval will be the same. For example, the person in the bus may be going from 0 to 2 meters per second in 1 second. If we figure out the change in velocity, change in time, we get 2 meters per second squared in the direction of motion. But with respect to Earth, adding in the idea that the buses, or whatever this is, moving 10 meters per second, that initially will be moving initially moving 10. After accelerating 2 meters per second, you'll be moving 12, as illustrated here. Still get the same acceleration. So position and velocity are different in different reference frames, but the length is the same, and also acceleration is the same. Okay. Before we go into this page, I think I'll stop the video there. And we'll take a look at part 2 when we come back. We'll see you shortly.